This is Calculus, March 23rd. We're starting section 9.7. 9.7 is just mixed review problems of the series you've been doing. So this is the video for that, and that's Fela. Say hi, Fela. Hey. Good job. There's Fela. All right, he's sitting here, just so you know, he's sitting here right next to our problems, just keeping us company. All right, so this is a good review that they have in this section. There's nothing new here. It's just you've got all these different tests. You know, unfortunately, they are all compiled for you in that nifty document that I have somewhere over here, probably with all the tests on it. Remember, this is posted on the blog, the one that says known series, and we have conversions, we have all the tests, we have nth term test. Be sure to read like everything they say, especially justification. What exactly do you have to write? Things I put in quotation marks are exact quotations you have to use. What are the limitations, advantage of each one? How do I know when I'm going to use which one? All those things are written in here. For the nth term test, the integral test, the two comparison tests, which are the regular comparison test. This is a shadow my cat. Come on, cat, get out of the light. The regular comparison test, the limit comparison test, the alternating series test, and our spanking new ratio test. Read through all of the different, advantages and disadvantages, and when to use them, how to justify them, because we need to decide which functions we're going to use and which tests we're going to use and how we're going to use them. So I'm going to just go ahead and tell you what I'm going to assign in this, which is page 710, that's 6-7 in your Stewart-Kokoska. We're going to do number 6 through 33, the multiples of 3. All right, that's what you're going to be assigned. So I'm going to do some sort of nearby problems. I'm starting with number 7. It's the sum from n equals 1 to infinity of n minus 1 over n cubed plus 1. So when we're looking at these, we want to think, well, the first thing you want to do is think, could I compare this to something? Well, I see that the degree of the denominator is 2 more than the degree of the numerator. So that sort of looks like 1 over n squared. So my thought bubble is this looks sort of like 1 over n squared. So I want to probably use a comparison test. And the question is, regular comparison or limit comparison? Now I know 1 over n squared converges. So if what I have here is less than 1 over n squared, then I can use the regular comparison test, which is easier. But if what I have here is more than 1 over n squared, then I have to use the limit comparison test, which is harder. So let's see. If I have n minus 1 over n cubed plus 1, well, if I think of n over n squared, well, I'm making the denominator smaller, the numerator smaller and the denominator larger. So what I have here is going to be smaller than that. That's actually an n cubed right there. And that n over n cubed is 1 over n squared. So I know that n minus 1 over n cubed plus 1 is less than 1 over n squared. And I should probably say for all n, but by the way, technically when you say for all n, you mean all n that are elements of the natural numbers. And sometimes we don't always write that in our justification, and it's important. All right, so now that I know that this series is smaller than a known convergent series, I can then wrap it up by saying sum n equals 1 to infinity converges because it is a p-series with p greater than 1, and sum from n equals 1 to infinity of n minus 1 over n cubed plus 1 converges. So here's what I have to say. I have to say by comparison test. So here are the magic things that I have to have in there. I have to have an inequality that establishes the relationship. I have to give a reason why the comparison series converges, and then I have to state that my series converges, and I have to cite the test that I'm using. All right, so that's your number 7. Yeah, I think we'll save number 13 for another video.